A very warm welcome to this webinar. Today we have three guests and experts. We're going to be talking about PFAS treatment in water. And as many of you know, it's not an easy thing to do. There's as close to 5,000 different molecules in this group of PFAS, and every year it grows as we find new ones and better ways for analyzing water and other media. So this is a very, very dynamic field of treating PFAS. The experts we have today is Hunter Anderson from the Air Force Center, Civil Engineering Center. He's a scientist and has taken up a very strong interest in PFAS. And for a lot of us in the industry, he's a person we look to see what's going on in the Air Force and what else we need to find ways to help with. Then we have Martin Cornelissen from Germany. He's the founder and the CEO of Cornelissen GmbH, which is a private company providing solutions for environmental problems, including how to treat PFAS in kind of nasty water streams. So Martin will tell us about that experience in Germany and the technologies that work there. Then we have David Fleming. He's the founder of TRS Group and also our technology leader for PFAS initiatives. He is the third panelist. This will be about 30 minutes of discussion, and you are more than welcome during this time to type in questions because after the formal part of the webinar, there is at least 10-15 minutes for us to address your questions. If we don't have time for all of them, or if we think what we replied wasn't good enough, we will follow up with written answers in about a week or less from today. So down at the bottom of your panel, you should have a place where it says Q&A, and that's where you click and it pops up a window where you can type in the questions, and they will arrive to us during the webinar, and in about 30-35 minutes we will go to those. So I'm kind of facilitating this by asking some questions, and I will start by asking Hunter, essentially with this very complex PFAS issue and the Air Force having a lot of sites, how is the Air Force dealing with this PFAS problem and when PFAS gets into water?
Yeah, so that's my cue. Hello, everyone. Happy to be here. Contrary to popular belief, I'll just start by saying that I'm not an expert in water treatment per se. However, I guess I am very much on the front lines of this issue and provide technical support for AFCEC's response to this whole emerging PFAS problem. For years, we've been in this business now for managing the whole PFAS liability. It kind of started with a slow march through the CERCLA process with the PASI effort. All that work's pretty well done. For the last year or so, we've been working our way through what we call these expanded site investigations. We're years away from any formal sort of remedy for soil and groundwater, but our interest in water treatment at the moment is almost exclusively relegated to the protection of drinking water resources for our on-base and immediately off-base down gradient receptor populations. And so the process of these ESIs, we do well surveys. We look at our conceptual models and determine who's potentially at risk within a 1 and 4 mile radius down gradient. In some cases, we sample those residential populations to determine if anyone is in fact being exposed. And if so, then we are immediately on the hook for time critical removal actions, which typically involve some sort of point of use water treatment. We're starting RIs this year. That'll be a long protracted exercise. Stay tuned for that. But I want to elaborate a bit on these ESIs. So next slide, Sarah. Specifically to respond to your question, Gorm, this is sort of the presumed issue out there. Every one of our installations has at least one source zones, if not multiple source zones. And in some cases, those are fairly large dilute groundwater plumes that we currently are aware of. We're not at the point where we can say much about what those plumes look like. We haven't done the characterization work, but in most instances, there is a down gradient residential population, and for where these residences are presumably impacted, we are taking efforts to mitigate those exposures. Next slide, Sarah. This is sort of a snapshot of the work we've done to date. This slide is out of date by about 6 months now due to the, well, I guess about 4 months now due to the quarantine and other issues. I just haven't had a chance to update it, but there's a handful of new dots that are on this map. But suffice it to say, from East Coast to the West Coast, Canada and Mexico, we're doing quite a bit of water treatment. And in these instances, like I said, they span the continuum of, just simply providing potable water and bottle services all the way up to full scale, million gallon per day type systems and everything in between. And so, we're very much in the business of water treatment with respect to what's going on across the industry. Next slide. And then the final thing I want to say here with regard to this sort of prelude before we get sort of more detailed type questions is, our primary focus is on PFAS and PFOA, of course, because of the lifetime health advisories and the target we have for, cleanup. But in reality, every single one of these sites is a really complicated mixture of vast combinations of PFAS, like Corin was saying. And I'm not convinced that all of these are necessarily problematic, but the real world reality is you have to be cognizant of these mixtures in order to make meaningful designs, and the fact that all of these sorbent materials are usually sort of confounded by, or at least the performance of these sorbent materials are confounded by the fact that there's other constituents in the water stream that are contributing to the loading of those materials. And if you're not mindful of that and how you sort of design and develop a strategy for your response, it's likely going to be a bit underperforming in terms of the observed breakthrough from what's anticipated. So this just sort of suggests this is all of our bulk groundwater data across all of our sites, thousands of detections across thousands of sites, quote unquote sites, source zones, where we have data to demonstrate that every single one of these sites without exception is a complex mixture. And that complex mixture, it turns out, is very important in terms of how you manage the response. So with that, I'll pause and we can move on with further questions.
Yep, fantastic. I just have one little quick question for you. You said sometimes you sample the people to see if they've been exposed. Is that a blood sample, or do you put them in a blender and then extract them?
Yeah, I meant to say their residences. Yeah, we don't sample anything but water off base, and typically it's at the tap. In some cases where there's a distribution system, we can kind of parse out, different parts of but no, I mean, there's no biomonitoring or anything like that going on. There is some of that taking place by our bioenvironmental group with respect to, occupational exposures from firefighters and stuff like that, but that's completely beyond my group's purview. We're exclusively focused on water samples.
Okay. So David, you've been in this business for about 30 years trying to find cost-effective solutions for environmental problems. What do you see in terms of markets? What are the types of areas where people have water problems where we may want to provide solutions?
Thanks, Gorm. Hi, everyone. Sarah, if you could go to the next slide, which is number 6. We think there are 5 primary market segments in this business. The first one being the change out of the aqueous film forming foams that contain PFAS, like firefighting trucks, changing out those foams, or airport hangars, or conveyance piping networks, or maybe storage vessels. And then firefighting water. So after an event has occurred, the fire's put out with these types of foams, and then now you've got a liquid that needs to be collected, stored, and treated. And then processed wastewater, both industrial and municipal wastewater. Industrial, for example, like a oil refinery, or some other type of industrial manufacturing process. And then on the municipal wastewater side, we're seeing interest from the end of the treatment, so after the filter cake has been dewatered and you're left with the rinse aid, or even from a reverse osmosis system. The final reject aid from reverse osmosis is another example of where that market segment is. And then landfill leachate. So leachate coming off a landfill, typically very complex. a lot of constituents in it, including PFAS. And then groundwater, pump and treat systems, treating high concentrations of PFAS in groundwater. And one of the other things that we're seeing now too are storage ponds, for example, at Department of Defense sites where, through firefighting training over the years, PFAS impacted water, AFFF, is stored in a pond on the base, and we're seeing interest in, how do you clean that up? And so that's another potential market segment.
All right. So that sounds like some pretty nasty water that you're talking about, pretty landfill leachate and other waste streams with probably high dissolved organic carbon, different pHs and all that. Martin, we know that you have a product called PerfluorAd. Can you please tell us how that works?
Yeah, thanks, Gorm. Hello to everyone from me too, and many thanks to TRS letting me participate to the webinar today. It's a pleasure for me. Yeah, to answer your question, Gorm, the PerfluorAd process I developed is specialized on the PFAS treatment, which show high PFAS concentration and also high organic background loads. That's the main topic why we developed this process. And in contrast to conventional treatment methods like the use of GAC or ion exchanger, the PerfluorAd technology is completely different. That means it's a different principle of action we use. It's not an adsorption, it's not an ion exchange process, but a precipitation process. We dose directly the active liquid ingredients, the PerfluorAd material, in the water stream and build in the water precipitation products. That means we create bounding between the anionic surfactant, that means a negative charged PFAS molecule, and the positive charged PerfluorAd molecule. Next slide, please. And this bounding leads to a changing of the solubility behavior of the formerly dissolved PFAS molecule. That means we build microflocs. And these kind of microflocs we can easily treat by the use of conventional filter methods like sedimentation processes or back filters. And very often we use sand filter to filter out these kind of flocks. Next, please. And I like to mention that the ionic bond between the PFAS and the PerfluorAd, it's just a weak ionic bound. And it's definitely not a chemical reaction which could form a fluoroorganic transfer product. There is no risk for this kind of building. Next, please. On the left graph, you see a conventional treatment filter system using normally minimum two GAC filter systems and upstream a sand filter to treat the iron, manganese, solids, whatever. And all we use to establish a PerfluorAd pretreatment is upstream an additional stirred reactor. We directly dose in the PerfluorAd material. And in this reactor, we create the flocks. We filter afterwards out in the sand filter, and behind the sand filter, we can see a significant reduction of the PFAS concentration. And this leads to the fact that we can dimension the GAC filter system much smaller than without the PerfluorAd pretreatment, and as well, the activated carbon consumption is much lower than without PerfluorAd treatment. Yeah, this is the main information I will give you to the question.
Thank you very much. So Hunter, this cannot be the only effective method for PFAS in water. What else are we looking at in the R&D world for this?
Yeah. So next slide, Sarah. There's a tremendous amount of, so in addition to sort of my day job as technical support for AFCEC, I also sort of wear a research hat upon occasion and provide Air Force sort of representation to the SERDP and ESTCP programs for the DoD. And those of you that aren't aware of these two programs, they're basically DoD's R&D wing or arm, $100+ million a year program across several different functional areas. But specific to restoration, we've been funding PFAS cleanup technology-based, research for several years now, and the number and breadth of the projects are far too expansive to list here. But suffice it to say, they're really relegated into these sort of three categories. We've invested a tremendous amount of money into the development of all kinds of different novel sorbents. Again, too many to list here, but organoclays, engineered silicas, all kinds of various polymers that people can manufacture specific to take or to capitalize onto these PFAS sort of specific properties, like Martin mentioned with respect to precipitation, the ionic fraction as well as the hydrophobic fraction, the size of the molecules, all of that sort of plays into how these sorbents work. A lot of that work is underway. Not a whole lot of it has, evolved to commercial maturity at this point, but a lot of work in the pipeline. The other end of the spectrum are with respect to destruction technologies. It's one thing to remove PFAS from water, but that just sort of defers the liability to some other waste stream. So we've also developed a lot of technologies to actually destroy this carbon-fluorine bond, which again is the most significant bond in nature. These technologies can be categorized as seen here, basically everything you can think of. And we're casting a wide net to see what works. But so far, we've got a lot of good preliminary results for plasma. Electrochemical oxidation is kind of on the fence. Hydrothermal work is coming on strong, and photocatalysis is another promising technology with UV activated sulfite materials. And then a lot of people are putting these technologies in combination in terms of these complicated treatment trains to remove the water or the PFAS from water with a very high flow rate, and then subsequently degrade those PFAS with periodic treatment of the waste stream. So a lot of work coming down the pike, linked here to all the different technology descriptions, but stay tuned for how all this evolves. Sure.
Thank you very much. And I may just add, I don't know if the conference is going to happen again this year, but going to the SERDP ESTCP conference for a couple of days towards the end of the year, it's amazing how much one can learn about what's going on. And so I highly recommend anyone who wants to stay up on it, go there and go every year, because we learn so much each time. Things are happening very quickly. And then a question for David. Going back to the PerfluorAd application, can you give us an overview of kind of the niche applications we see for that? What types of water streams that is best for?
Sure, of course. Sarah, could you advance to the next slide, please? Number 12. So the niche applications for PerfluorAd include high PFAS concentrations, and we're talking about 50 micrograms per liter total PFAS and higher. However, there has been recent data generated from some laboratory bench studies from an industrial process manufacturing facility that showed very low initial concentrations in the double parts per trillion concentration range, that PerfluorAd was very effective at reducing those by 99%. So typically the technologies for the higher concentrations and also dissolved organic carbon, if you have high dissolved organic carbon in your water, it doesn't interfere with PerfluorAd. So that's one of the advantages of PerfluorAd. Plus very dirty water, as you can see here on the screen. This is a beaker of some dirty contaminated water from a fire event with a bunch of different contaminants in it, including petroleum hydrocarbons. You could have chlorinated solvents and other constituents that don't really interfere with the PerfluorAd ability to make that bond with the PFAS to create the particles. And then firefighting systems, as I mentioned earlier. This is a niche where we're exploring more in the US. It's been proven in Germany many times by cleaning out firefighting trucks with the PerfluorAd system. Very effective at getting the PerfluorAd, or excuse me, the PFAS and the AFFF out of the the firefighting truck very effectively. Next slide, please, Sarah. And here's an example of treating firefighting water with PerfluorAd. On the left, you've got in that chart the composition of the firefighting water after the event of putting out the fire. And this is a polymer or foam called 1% concentration of Mausol, APS 1/3. So this is in concentration milligrams per liter. This is after the event. And now you've got these 7 components in the firefighting water, 23 PFAS substances, capstones, which is another polymer added to firefighting foam. You've got adsorbable organically bound fluorine, organic bound fluorine, 100 milligram per liter of organic bound fluorine, cationic surfactant, also anionic surfactant, and then very high concentration of dissolved organic carbon. And that's primarily because there was a lot of fuel in this fire. So there was a TPH in there that created a lot of this dissolved organic carbon. And you've got pretty high concentration of PFAS, those 23 substances, 2 milligrams per liter. On the right are the elimination rates. After adding 2 grams per liter of PerfluorAd into this extinguishing or firefighting water, you see the corresponding reductions in each of these 7 components, 99.3% of the total PFAS. And all the way over to the anionic surfactant, very high percent reduction, almost 100% reduction of the anionic surfactant. And then you can see the green there, the 34.2, that's the cationic surfactant. So not as good a reduction because, positively charged molecules don't create that ionic bond as well as the negative and the positive from the anionic surfactant. And then the other point is the dissolved organic carbon. See how little interference from dissolved organic carbon there is, only 1.1% elimination. So that's another advantage of PerfluorAd, where dissolved organic carbon does not interfere with the elimination rates of using PerfluorAd.
Thank you so much. Martin, we know you have had a head start on this in Germany. Can you please show us, some of the projects or some examples of PerfluorAd applications so we can get a feel for what it looks like?
Yeah, sure. Before I show you a concrete example, I would like you to show a map with the project references in Germany, Netherlands, and Luxembourg that have been worked out so far. There are almost 20 projects that we have implemented with PerfluorAd since the market launch in 2015. Just to mention it, yeah. As I mentioned earlier, the PerfluorAd process has been developed for the treatment of water containing high PFAS loads and or high DOC contents. This is not to say that this process cannot be used for low PFAS loads, but the technical efficiency and the cost advantages of these processes are shown especially in highly contaminated waters. That's important to understand. Such as landfill leachate waters, David already mentioned this, heavily polluted groundwaters, as well as industrial wastewater with high organic contents, firefighting water, and several more. I cannot show you examples, project examples for every kind of waters I mentioned before, but I like to highlight application case which is currently of great relevance in Germany. This is the use of the PerfluorAd technology for the cleaning of PFAS contaminated firefighting trucks. Next, please. The cleaning process of firefighting trucks is normally carried out in 3 steps. In the first step, the AFFF tank and all piping, all valves is completely emptied of the foam concentrate. This is shown in the current picture. We have to use a lot of hose lines and do a lot of manual work to empty the trucks completely. And then in the second step, please next slide, we establish a rinsing circuit with fresh water enriched with PerfluorAd. And try to clean up each pipe, each pump, and all tanks inside the firefighting truck, like shown in this simplified scheme here. Next, please. And in the third step, the rinsing water resulting from this cleaning process, which is very often extremely contaminated with PFAS and as well organic matter, is treated on site with another use of PerfluorAd. And in the next slide, I show you a picture of such a treatment plant we very often use for this kind of work. This photo shows in the front the blue reactor. It's a batch reactor. We first use for to collect the rinsate from the cleaning process, and then in the second step we treat the water inside this batch reactor. You see on the bottom of the reactor 3 funnels in which the formed PFAS perfluoride flocks are sedimented, and the 2 small silver vessels on the right side of the picture, these are back filters which are used to filter out the remaining flocks after the sedimentation. And the small blue vessel behind the filter, but the back filters, is a gag filter to polish the water treated with perfluoride. You see that the complete water treatment process with perfluoride is therefore very simple. And the whole treatment process of such highly contaminated waters becomes absolutely manageable by the use of the PerfluorAd technology. And this is not only valid for this highly contaminated water coming from the cleaning of the fire trucks, but also for all other water qualities.
Okay, I think I will throw in a quick a bonus question, and Hunter, you're more than welcome to pitch in as well. There's been 5 or 6 questions already in the panel asking what happens to the treated adsorbent, in other words, the flock PerfluorAd with PFAS in it, or if you're using carbon or any of the other adsorbents, Hunter, you described. When you got all the PFAS concentrated in a small volume, where does it go? What happens to it?
I don't know if I get right of refusal there or not, but I'll start, I guess. Yeah, so for the last several years, to include our AFFF stocks, everything in the solid phase, and even a lot of dilute liquid waste streams have gone to the incineration facilities. And although that's sort of becoming a taboo thing, and we're getting a lot of, I guess, bad press for doing that, the emphasis here was on water treatment, so I didn't elaborate. But through SERDP and ESTCP and collaborations with EPA, we've got a tremendous amount of work that's coming down the pipeline that's yet to be funded because it's a this year SON problem. But we've got a tremendous amount of resources being devoted to the incineration science, and exactly what types of temperatures and what residence times are sufficient to fully mineralize all these concentrated waste streams. But again, as I mentioned, we're exploring all these different novel treatment trains to include, non-thermal plasma, electrochemical oxidation, all these incineration alternatives. And so to the extent that those technologies, prove out and then become commercially available at the scale that's sufficient to manage these, waste streams as they're produced in practice, remains to be seen. But that's the idea, is we have a whole market portfolio, and then we just let the economics and the regulations dictate what we do with it.
Okay, good. I assume one of the ways that make this feasible is that, let's say you have 1,000 gallons of very contaminated water, you have maybe a few gallons of waste that you're actually incinerating, instead of having to burn the whole water stream, which would be incredibly expensive.
Hey, Gordon,
obviously, the more.
Go ahead.
Sorry. Well, obviously, the more concentrated the waste stream, the better, for sure.
Yeah. Okay. So,
could I add one visual? So, if you can imagine, like a swimming pool, water in a swimming pool with PFAS in the parts per billion range. The largest project I think Cornelison has performed is on the order of 80,000 gallons continuous flow of water contaminated with PFAS. Part per billion range to begin with, double digit. And then after the PerfluorAd treatment, flocking out the PFAS, filtering it out, what you're left with is on the order of less than a coffee cup full of residue. So that's a good image, I think, that is for me at least sticks with me, and just as an example.
Okay. Is this technology available in the US? Yeah, we saw like 18, 19 dots on the German map, but what about over here?
Yeah, so Sarah, could you advance to the next slide? That's number 19. So TRS is the provider of PerfluorAd in the United States. And what's available are bench studies. We're doing laboratory bench studies. And that's important in order to understand the chemistry of the water, as well as identifying the ideal dosing rate of PerfluorAd based on that water chemistry, including the PFAS concentrations, to create the best reduction of PFAS in the water. So that's on the bench scale side of things. And we're doing those in Germany. We're using Corneliussen's vast experience to help us really perform these studies. We feel like that's the best way to do this. So many customers we're working with to provide samples over to the Corneliussen lab in Essen, Germany, to perform these laboratory bench studies. And then we're building, or Corneliussen is building, a pilot test system for the US market that we're expecting to be delivered early this fall. And that pilot test system comprises 4 Connex boxes that are each 20 feet long. They'll be shipped on a tractor trailer. 2 trucks come in shipping these components. And what they're consist of, the first system, as you can see the pictures here at the bottom of the slide, the PerfluorAd process. So you've got the tanks, the stirrers, the dosing equipment inside the first box. Second box is the filtration and backwashing components. And the third box is separation and belt filtering components. On the fourth box then is going to be the control panels and the programmable logic controllers. So 4 boxes representing the pilot test system. Can you go to the next slide, Sarah? So I want to show you an example of a test or a project that was performed at the Essen Corneliussen facility in Essen, Germany. And you can see this is a fire truck, gentleman on top of the truck, shaking it back and forth. And what he's doing is he's agitating the truck to get the PerfluorAd that's inside the truck in contact with the AFFF and the PFAS inside this complex network of piping and pumps inside the truck. And that's very important because if you don't get out the majority of the PFAS, once it's being replaced with fluorine-free foams, you run the risk of recontaminating that foam. And we have found in Germany, this is a very good way of cleaning out these trucks on the order of, in this case, 99.99% reduction of total PFAS. And we're about ready to embark on a similar type of a test in the United States to prove this out as well.
Thank you very much. And we have one more canned question, if you will, before we open it up to Q&A from the panel there, or from everyone who's written. And this is for Hunter. So what is probably the most difficult question of the day? So there's 4,000 or 5,000 different PFAS molecules. Which ones are we targeting, and what's the implication of us finding new molecules all the time? And of course, a lot of people think about the shorter chain PFAS molecules that are now being added to the mix. Do you have any thoughts on that?
Yeah, sure. That is quite a loaded question. Sarah, if you go to the next slide. So as I indicated previously, each one of these AFFF impacted sites is truly a mixture. And I think that's going to stand across, the world in terms of all the various sources of PFAS emissions, whether it be from manufacturing, what have you. But very rarely are you going to have a situation where there's, a few single, or a few PFAS to manage. Usually it's these really complicated mixtures in very different quantities and compositions across the sites. And the question does come up when we build these systems. It's one thing to target the long chain perfluorinated compounds like PFOA and PFAS that are relatively easily removed by absorption and things like precipitation. But it's another thing altogether to start talking about removal of the short chain species. And again, I'm not convinced that they're all necessarily problematic, but these questions come up in the interim as we're designing this system. To what extent are you going to prescribe long-term O&M to be inclusive of these short chain compounds? To kind of answer that question, we partnered with the EPA not too long ago, some folks in Cincinnati at the Office of Research and Development, who have built and managed their online drinking water treatability module to now include PFAS. We can model the breakthrough of different simulated systems across a range of different scenarios, site conditions. So we've kind of done this little desktop exercise and illustrated that relative to just being considerate or inclusive of PFOA and PFAS at the LHA, meaning when we prescribe changeout, media changeouts, when we observe breakthrough at the LHA, if we alternatively prescribe changeouts at any detectable PFAS or PFOA versus any detectable PFAS, we see upwards of orders of magnitude inflation in cost multipliers. So if specifically if we're inclusive of the short chain compounds, the red curve on this figure, depending on things like flow rate, empty bed contact time, the water chemistry, a range of other considerations, it's very rarely the case that the costs are trivial. So really what we're looking for in a technology, a silver bullet technology, is something that's not only cost competitive to the conventional sort of GAC benchmark, I would say, but something that's more effective, relatively speaking, for the short chain compounds as well. And I'll leave that at that, and we can follow up on this if anybody would like. But it's a fairly complicated question with a fairly simple answer. It depends.
Very nice, thank you. And it's now open mic time, and I'm going to look through the questions, mostly in the Q&A group, but I see someone has also asked questions in the chat, so forgive me if I'm a little slow to find them. And any of you panelists are more than welcome to pick one and just start talking when I slow down. But one that stood out right away was, other than the one we just addressed on what happens to the waste, was on PerfluorAd as well, and whether it works on landfill leachate. We did show that in a slide, overview slide, but do we have any data to back up that we can actually treat these low levels of PFAS in landfill leachate?
Yes, if you go to the next slide, Sarah, there's a good description of the landfill leachate, Martin, that maybe you want to address.
Yeah, it's just an example for a treatment of a landfill leachate. We did some tests by the use of different amount of PerfluorAd. We show here on the x-axis, we started with 10 milligram per liter and reached these elimination rates for total PFAS. It's not that much, only approx 30% for total PFAS, but with this small amount of PerfluorAd used, we reached already nearly 100% for PFAS. Yeah, that shows very, very clearly that the PerfluorAd is specialized on the anionic surfactants. Yeah, so, and by increasing the dosage, you see that we can increase the elimination rate as well. Yeah. So you see the PFAS elimination rate right on the dark yellow bar, and PFOA is the violet bar, approx more than 19% for PFOA, nearly 100% for PFOS using 40 milligram per liter PerfluorAd. It's just an example, but yeah, depends from case to case. But very often for the long chain PFAS, we reach nearly 100%.
Yeah. So I have a follow-up question. It's also one from the listeners, but I'll rephrase it a little bit. It basically is, the question is how much PFAS is left in the water after it's gone through this PerfluorAd treatment. And I can ask it a different way. Do you need to polish the water with carbon at the end? Are you close to drinking water standards when it is pre-treated with PerfluorAd, or what levels? Are we in the tens of ppt, or where are we when we're done, when it goes through the pre-treatment?
Yeah, it depends on the specific requirements. Yeah, in Germany, it's pretty common that the environmental authorities ask for a polishing step using activated carbon. Yeah, but very often we reach the required target levels only by the use of PerfluorAd. And then the polishing step it doesn't make sense at all, but it's very often required. Yeah. So it's possible in general, if the target values are not zero, that we can reach only by the use of PerfluorAd the target values, and do not need a polishing step.
Thank you very much. Another question came in asking if, maybe I'll take one that's not PerfluorAd related, to break it up a little bit. One question basically came from Latin America and said, is it also common down here? And another question was about, what about the rest of the world? Is there PFAS problems coming, and have PFAS been used in those firefighting foams kind of everywhere? I don't know if anyone has, of you three have looked at that, but it's a good question. Is that going to be in Brazil, for instance, in China? We know.
So yeah, it's definitely a global phenomenon. I mean, every country, every developed country who's ever used any kind of advanced firefighting foam technologies got PFAS liability. Canadians, Australians. I've personally been to Australia and seen a number of their sites. I interact with a lot of Europeans. You know, even some of the third world are starting to realize it now, because as the developed countries have slowly weaned themselves off of these fluorosurfactants, we push all our stock on the third world, where the regulations are scant. And so, you know, it's clearly a global problem. And if you look at sort of the distribution of where all the research is done, people doing current studies and stuff, every corner of the planet is basically contaminated with some degree of measurable PFAS, to include Antarctica and the Arctic. It's a worldwide problem, to say the least.
Yeah. A little very technical one on PerfluorAd, and it's hard for me to say this word, but the Swither ions, so the molecules that have both a plus and a minus charge, does it work for those as well, and how?
Yeah, I like to jump in. Yeah, we can treat the Swither ionic as well, but to be honest, we do not reach these high elimination rates we can achieve maybe for PFAS and PFOA. Yeah, we can reduce the contamination, but it's the application, the liquid active ingredient PerfluorAd is not specialized on the Swither ionic structures, but on the anionic ones. Yeah, so very often we reach elimination rates for the Swither ionic of about 50, 60, maybe 70%, but definitely not 100% elimination. So in this case, we need to have a polishing step behind the PerfluorAd stage.
Mm-hmm. I see a lot of questions have landed in the chat bar, so I got to go over there too. Is the PerfluorAd approved by the EPA? That was a direct question. Is it approved for use?
Not specifically. I mean, we have not gone through a process in the United States of getting any type of approval from EPA. However, they're very interested, as the Department of Defense is, in finding solutions and willing to test these different techniques, including PerfluorAd. So, I mean, we're seeing a lot of interest in proving it in the United States, both in the laboratory as well as in the field, but there hasn't been a specific formal process that we've gone through to get EPA approval. Now, that may be different in Germany with the German equivalent. Martin, I don't know.
in Germany, or let's say in Europe, we have a environmental agency called ECHA, and there are the main active components of PerfluorAd are listed and approved there from this agency. Yeah, so we do not need to have a separate permission.
I guess one thing also to keep in mind is that the PerfluorAd substance is actually a plant-based oleic acid.
Yeah,
it's biodegradable.
Yes.
So I mean,
correct.
You know, in terms of the definition of sustainability and some of these others, I think it's seen as very favorable. Yeah.
Dora put in a question concerning biodegradation of PerfluorAd. Maybe we can pick up this question from Dora now in this context.
Yes.
Hello, Dora. It's like David mentioned before, it was very important to me to develop a biodegradable active ingredient, not a hazardous one, to solve the PFAS problem. So it's important that we separate the builded PFAS PerfluorAd flock from the water treatment system after the flock building process is finalized. That means we separate the flock from the water, and then it doesn't matter that the biodegradation process of the PerfluorAd starts, and then the PFAS is released, because we have separated the flocks in a very small volume. And this volume we want to treat by a discharge or disposal in a high temperature incinerator plant, or the use of other electrochemical methods or whatever. Yeah. So to answer the question, we separate the flock, and if the biodegradation process starts, it doesn't matter there.
Mm-hmm. Very good. We've come to the end of this this webinar. The time is gone, and I don't see a whole lot of unanswered questions. There are a few that we will answer by, in writing, I believe. Do you guys have any additional closing things to say, or should we just round it off here?
Maybe if it's possible to answer another question. Yeah. Mitch put in a question concerning the fire truck cleaning. Mitch asked if the truck then tested after the cleaning process.
Yes.
Yes, we do this. We collect the water sample before the cleaning process and afterwards. The final step is a final rinsing process with only fresh water, and this fresh water is also analyzed on PFAS. Yeah, so yeah, this is the procedure we realize in Germany. Yeah.
And Sarah, if you will go to slide 28, there's actually some data summarizing a change out.
Yeah, that's a good point. That's the data that Sarah's bringing up is from that firefighting truck video we showed earlier from that project. 28, yeah.
Down.
But what you'll see is equivalent of 99.99% reduction. I think it's the next one after that. There you go.
That one, yes.
You see you're starting with on the order of 40,000 microgram per liter of total PFAS. And somebody asked earlier, I think too, how do we define total PFAS? And it's been on the order of what, 19 to 23 compounds, something like that. Depends on the analysis that's being done, but that's the range. And as you can see, after the PerfluorAd treatment, knocked it down almost 100%, down to less than 2 micrograms per liter. And that was one fire truck that was cleaned out with PerfluorAd.
Mm-hmm.
Mhm.
Just to mention it, only by the use of PerfluorAd, not with the polishing step afterwards. It's just the result by the use of only PerfluorAd.
Yeah. We also had a question on cost. What is the cost to treat 1,000 gallons? And I know that's a very difficult question to ask because it completely depends on scale. I think we will refrain from opening that can of worms on this particular webinar, and maybe there'll be some other chance to talk about it. There's no doubt that, you know, if all we have as best available technology is just activated carbon, that then we are going to be building some enormous treatment plants that will use a lot of granular activated charcoal and create a whole lot of waste with PFAS in it for destruction, and that we're all working hard to find ways to lower that cost, because that's not a fun thing for Hunter and his colleagues to think about having to do at all these sites, right? Building these 10, 100, 1,000 gallon per minute systems that will have to run forever, and carbon being spent quickly. So more on that later, but in Germany, according to the 19 case studies, it seems definitely to be cost effective over there to do some pre-treatment, so you don't just use carbon for everything. And we're still, you know, early days in the US proving that out, which is in the process now.
Mm.
Thank you.
And with that, I think we'll conclude this. We will follow up with some written questions or answers to your questions. And thank you everyone for tuning in today.
Thank you all.
Thank
Take
you.
care. Be safe.
Thank you.
Bye, Martin. Bye, Norm.
Bye.
Thank
Thank
you.
you. Thank you. Bye.
Talk to you tomorrow.
Yeah, see you.